series on the left-hand side is actually the even part of the generating function of q1 star minus q3 star.
Can you just remind some people quickly what minus q to the sub n?
Oh, all right. So minus q sub 2n is 1 plus q squared dot 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 up to 1 plus q to the power of 2n from the previous page. Okay, that notation. So what I'm saying here is if I replace q by q squared, this expression here is actually the even part of the generating function q1 star of n minus q2 star of n q power n. If you look at the even part, that's what you would get. And the second series would yield the odd part in a similar way. So what Ramanujan had written down in these two series were actually lacunary representations for the even and odd parts of the difference that generating function for the difference that Find was looking at. So Find's theorems are embedded in these identities in Ramanujan's last notebook. But Find can be excused because Find discovered this in the middle of the 20th century, and Ramanujan's last notebook was unearthed only in 1976 by George Andrews. So when Find wrote them down, he was unaware that Ramanujan had written these. Okay. Now, this also brings to one's mind the statement of Bill Gasper, who I think would be an ideal speaker for the experimental mathematics seminar, who said, Ramanujan has this tendency of reaching out from his grave and snatching away your best theorems. So you prove some wonderful theorems, and then it turns out that they're embedded somewhere in one of Ramanujan's writings. So this is the sort of thing.
But the commutator interpretation was not in Ramanujan.
No. And that is another thing. Ramanujan also seldom wrote down combinatorial interpretations of his results. All right. Now, since I mentioned 1 plus zq to the m, the question arises, is there a way in which the Pentagonal numbers theorem of Euler can be refined by the introduction of a parameter? The answer is yes, and I'm going to give you two versions. One goes back to Sylvester, who put a parameter z here and wrote down such an expansion. Now, this expansion Sylvester derived purely combinatorially by studying partitions in terms of what are called Durfee's squares. If you take the Ferret's graph and you look at the largest square sitting there and you classify partitions according to the Durfee squares and you do some calculation, you will end up with an expression of this type. After Sylvester derived this, he posed a challenge to the mathematical community saying, I have found this purely combinatorially. Is there a purely Q-series proof of this? Meaning, what would be a Q-series proof? An example. Suppose I replace z by zq. Let's think of the left-hand side as f of zq. If I replace z by zq, I'm getting the product, but I've lost the first factor. So you can now think of f of zq, comma q to be all of f of zq divided by 1 plus zq. And so that's sort of a functional equation. Can you manipulate the right-hand side to show that that has got a similar functional equation? Then you check your initial condition. That, for example, would be a Q-series proof. That's the sort of thing that Cayley did. So he picked up Sylvester's challenge, but it took some time. So this is, again, to stress.
So Sylvester didn't call it Q-theoretic. How?
He, I think, said, can you give an analytic? I'm using. But it was still Sylvester's challenge. I mean, what he did was combinatorial, and he wanted something that would only involve the Q-theoretic.
You say the other way around.
Yeah. Now, so this is something also that is worthwhile. That is, people always think that if you have a Q identity, that its combinatorial understanding is automatic. That's false. And similarly, if you prove something combinatorially, the fact that you can get an analytic proof is automatic is also wrong. So sometimes these are deeper. Now, if you put z equal to minus 1 in Sylvester's identity, then of course the product is the one on the left-hand side here. Then you get this, but here you see cancellation. This cancels into this, leaving a last factor 1 minus q to the n. That goes into that, giving you 1 plus q to the n. So you get this series, but now this is really making it bilateral, and you end up with the Euler pentagonal number series. So z equal to minus 1 in Sylvester's identity is Euler's pentagonal numbers theorem. But it's very interesting that even though Sylvester derived his theorem combinatorially, neither Sylvester nor many of his successors stated the actual partition theorem, which is equivalent to that identity. So you see there are two things. You can prove an identity combinatorially, but that doesn't necessarily mean that you have captured it as a certain partition theorem. Okay, so I was a new entrant to the theory of partitions, and George Andrews sent me a stack of papers to read, and one of them was Sylvester's paper. And I looked at it, and I never found an interpretation of this theorem. And I looked at George Andrews' encyclopedia, which had wonderful theorems, and I never found an interpretation of this theorem. So as a student, I said, what does this identity mean as a partition theorem? Okay, so I'm going to give you the partition interpretation of this identity. So this partition interpretation is weighted, but this is something very interesting. So here's what you do. The series part of Sylvester's identity is dealing with partitions into parts that differ by at least 3.